I'm going to try and give perhaps a rather foolhardy idea. I was going to try and explain to you the kind of mathematics I do and the kind of ideas that seem to me simple and enable me to think about the the problems that I think about. I realize that for me, these ideas of simplicity, you might say, the way I'm using the word, it's almost synonymous with finding structure that you can think about. Okay. Oh, you've got a microphone. Great. Thank you. It's on. Okay, so I can move away. So I'm a geometer. So that means I study, topologist geometer. Topologist studies the structure of space, and a geometer studies the structure of space, but you put extra, you make measurements in space. So it's not just sort of empty space, but you allow yourself, say, to measure the length of a line, or to measure angles, or to make other measurements. Now, in symplectic geometry, you make a rather idiosyncratic kind of measurement. You measure not one-dimensional things like the lengths of lines, but you make a two-dimensional measurement. If you have a little bit of surface, you measure the area of that surface. And I want to explain to you a little bit why that's interesting. I mean, why would one ever do such a thing? And then explain to you that, try and explain to you that in fact, a lot of modern topology, you don't just study sort of plain vanilla spaces because they're often too complicated to understand. You do put extra structure on them as a way of helping you understand. For example, the solution of the three-dimensional Poincare hypothesis was achieved by people putting a metric on the space, which is a metric means that you can measure the distance between any 2 points. It's a linear measure, and by looking at the properties of these metrics that you put on space and various complicated differential equations, some flows, natural flows they satisfied, people were able to finally solve one of the main problems in three-dimensional topology, which was if you have a shape which looks as though it should be a sphere, something really simple, to prove that it truly is a sphere. Now, there remain similar problems in 4 dimensions. And so that's what I'm mostly going to talk about. In fact, with this kind of problem becomes easier in higher dimensions. Because there's just more room to do things. So that's one of the reasons that 4 dimensions is interesting. Another reason that 4 dimensions is interesting is that for the kind of structure I look at, which is a symplectic structure, that's sort of the first interesting dimension. So let me tell you a little bit, first of all, about what dimension is, because I know you're not all mathematicians, and so when I talk about spaces of a particular dimension, what do I mean? Well, 1 dimension, that's easy. That's just a line. We're just hearing about the line, an infinite line which we think of as the real numbers. So we can describe a line by just taking a point and numbering where we are, how far we are along the line, positive and negative. So this fits very well with the previous talk because this was the notion of time they had, the timeline. So that's a 1-dimensional space, but you can sort of wrap it up in itself and get a circle. That's also a 1-dimensional space, which a little piece of it looks like a little piece of the line. So that's a 1-dimensional space. Now, a 2-dimensional space, that's also easy to understand. A 2-dimensional space, a typical thing would be the surface of this blackboard, where you say it's 2-dimensional. Well, one easy way to say that is that if you want to describe where you are in the space, you need 2 numbers. You need one number which tells you how far you've gone in the x direction, and another number which tells how far you've gone in the y direction. So you've got a pair of numbers, x, y. That makes it 2-dimensional. And, for a simple description of what's a 3-dimensional space, well, you need 3 numbers to describe where you are. You need to go up, along, and in this direction, 3 directions. And in 4 dimensions, you need four coordinates and so on. So that's a notion of dimension. So we'd write something like R4, which would be 4-dimensional plain vanilla space, and you describe it by means of 4 coordinates, x1, x2, x3, x4. That's a sort of these would be the set of points you describe with this data. And then the more complicated, wrapped up forms of 4 dimensions, you'd locally have something which looks like this, but globally it would twist around. And you might want to know, how does it twist around? What are all the possible ways of it twisting around? Now, in 2 dimensions, of course, you can draw the pictures. You can say, okay, we could have a surface of a sphere, which is just the surface of a ball. That's a ball, a sphere. And this is a sphere, and this is a surface of a donut, or what's called a torus. And you can just draw them in 3-dimensional space, what you get. In 3 dimensions, it becomes much harder. You can't draw them in 3-dimensional space because you sort of run out. You've got your little piece of 3-dimensional space, and then to describe how it curves, you have to go out of our standard 3-dimensional space. 4 dimensions, it's even more of a problem because we have 4 dimensions to think about. Now, as I said, I don't study sort of plain vanilla spaces, but I study spaces with a particular kind of structure on called a symplectic structure. And, this structure was first thought about in the 19th century, as far as I know, by William Hamilton. And he was interested in understanding the equations of motion. He wanted, if you have a planet moving around the sun, he wanted to understand that motion, or the motion of those days they understood that, so it was more like the motion of tops, or something more complicated, the rotation of tops. And what they understood, this is a kind of motion that conserves energy in an ideal situation. And for energy-preserving flows, there's some kind of structure underlying the equations, which is a symplectic structure, that can be used to simplify the equation. So if all you're interested in is purely computational problem, here's a top, I set it spinning. How can I describe what it does? It does all sort of complicated precessions and wanders around the floor. It does all kinds of things. If you want to simply describe and solve those equations, using the symplectic structure turned out to give you guidance as to what choices of coordinates you should use to make the equations so they were solvable. Because if you just looked at it, the equations were far too complicated to solve. So this actually began as a sort of computational device. But then later on, people realized that it was one of 5 basic kinds of geometry there are. You can measure lengths and get what's called Euclidean geometry. You can measure volume, which is a very natural thing, just the volume of something. This is a 2-dimensional measurement, which is based on areas. And, because it's a 2-dimensional measurement, the geometry lives only in 2 dimensions, in 4 dimensions, in 6 dimensions. It's an even-dimensional geometry. And in 2 dimensions, if you have a little bit of surface, the symplectic form is traditionally called omega. What it does for a little piece of surface, it's just its area, which is given a sign. So you could take the area and then sort of flip the thing over and it would become negative. So it's not just a positive number. It could be negative. But in 4 dimensions, what do you do? You're still making 2-dimensional measurements. And so what you do, if you're in R4, you take a little bit of surface, which is something 2-dimensional. That's 2-dimensional. And you project it. You just think of shining light and just project it onto, say, the first 2 coordinates, which you think of x1 and y1. You get some piece of a 2-dimensional object, and you measure its area. So the symplectic form is the area of the projection in the 1-2 direction. And then you also, to make it sort of symmetric, you project into the 3-4 coordinates, which I'm going to write x1, y2. You project there, so this is the projection of x1, y1. You add the area of the projection onto the other 2 coordinates. So this looks like a very funny measurement. You see, you're taking something 2-dimensional, which is sitting in 4-dimensional space. You project it onto the floor, say, and measure its area, and then you project it into the other 2 directions, which you can't quite see, and measure that area. Take the sum. And it's hard to see why it has meaning, but it does have meaning. And one of the things is, you see, when you're studying the motion of something, as I say, it arose from trying to understand motion. if you have something which is moving in one dimension, suppose you have a particle moving just on a line, it has two relevant numbers. It has one number, x1, which is the position, and it has another number, y1, which is its velocity, the speed, how fast it's moving. And if it's moving in such a way, just with conservation of energy, if you know those two numbers at some time, you know those numbers for all time. But you need two numbers to describe motion in a single direction. So if you have motion in the plane, like if you have something like moving around in the plane, you need four numbers because you've got two numbers to describe the position and you have another two numbers to describe the velocities. There's two velocities. There's one, you see, you've got a position, which is x1 and x2, and then you've got y1 and y2, and these are the corresponding velocities. So y1 will be the amount it's moving in that direction, because movement's got a direction. So you could move in this direction, you could move up. So you have to have two numbers to describe the position and two numbers to describe the velocity. And what this is measuring is some kind of relation between the position and velocity in one direction. You add that, and you take a measure of the position and velocity in the other direction. And that's what you're measuring. That's your measurement. And it turns out, it's hard to, I can't possibly explain really, but this turns out to be a very important measurement. It's a very important structure, this structure of symplectic geometry. But it's very much a two-dimensional structure. Now, what is a simplifying idea you can use? Well, you see, I've described geometry here using the real numbers as our basis. The real numbers is just it's a line, it's complete, it's got order, but there's another set of numbers which I want to talk about, which are the complex numbers. Happen to be called complex. The complex numbers, or the imaginary numbers, you take the real numbers, they form a plane, the complex numbers. These are the numbers where you add in the square root of -1. So you have a number I, which has the magical property that when you square it, you get -1. If you start with a real number, you know all squares are positive. But you can add, this was probably, I don't know, I'm not very good at history of mathematics, but people were slowly discovering the importance of this idea like in the medieval times. And they thought it wasn't a proper number. They hardly thought that negative numbers were proper numbers, and they certainly didn't think these were proper numbers. That's why they were called imaginary numbers. But the amazing thing, you can add that, so your numbers now look something like 2 plus 3 times the square root of -1. So you have a real part and you have an imaginary part. And so you can picture these numbers on the plane because you have the real part, which is a 2. You can have 2, and then you can have 3 to describe this number. Because I is sort of the coordinate there, and the real part is there. So these numbers are on the plane. And it's not very difficult to see you can add them, but it's really quite surprising that you can multiply them and divide them. So you get a set of numbers which have all the properties of the real numbers and the sort of arithmetic properties of the real numbers. And then, you see, I have always thought that complex numbers are magic. And one of the reasons is that magic is this. You've added just this one number, and then you've added other things so you can add two together and multiply. If you add that number to your system and you take the equation x squared equals -1, if you just try and find real numbers satisfying that, there are no solutions. But -1, the square root of I, is precisely a solution of this equation. So what you've done is you've added a number which solves this equation. Now, the magic thing is, if I write down any other polynomial equation, like, 3 times x to the 5th plus pi times x cubed minus root 2 times x plus 59, and I want to solve that equation, I can solve it if I allow myself complex solutions. And in fact, it's got exactly 5 solutions, counted correctly. So the thing is, you add one number to solve one equation, and you get a set of numbers that solves all possible polynomial equations. So I think that's magic. These are really powerful sets of numbers, and they're two-dimensional set of numbers. Now, there are other magic things about complex numbers, which if anybody knows any calculus, there's a notion of a function is differentiable if you can sort of measure how fast it's changing. So if you have a function of a complex number, there's a notion of to make it differentiable in a complex way. And those are called holomorphic functions. And they have amazing properties. So if you have a holomorphic function, which is basically just a complex differentiable function, then if you know that function in one little piece of the plane, you know it everywhere. Just its values, actually just its values and all its derivatives at a point, tell you what it is everywhere. So there's an amazing uniqueness and rigidity about this. That, I should have told you what a function is. A function would be something that to every complex number gives you another complex number. So if I put in a complex number, it's a sort of input-output device that given one complex number gives you another one. And normally, of course, all these values are completely different from each other. But you could ask for nice properties of this function, like it's continuous, so that if this moves a little, that moves a little. You can ask that it's differentiable, so you could measure its rate of change. And if this function is differentiable in the sort of complex sense, then it has this amazing property that you know its values just at near one point. You know all its values everywhere. It's a very rigid kind of thing. And so complex geometry has a whole lot of structure. It's a very rigid kind of geometry. Now, one of the interesting things about symplectic geometry, it has a really deep relation to complex geometry. See, it lives only in two dimensions. It lives only in even dimensions. And say this four-dimensional geometry, R4, I've already grouped my coordinates into pairs. I've got x1, y1, and x2, y2. And I can, out of those pairs of numbers, I can make two complex numbers. I can write this, think of this as the real and imaginary parts of a single complex number. So I could write z1 equals x1 plus I y1. And I can write z2 similarly is x2 plus I y2. So out of four real numbers, I can make two complex numbers. And that means that instead of thinking of my space as four-dimensional, I can think of it as two-dimensional. There's only 2 bits of information I need. That's a huge simplification. And of course, you can say, well, okay, you can do that, but does it have any meaning? When you start moving the space around, do you still see the structure? You want your structure to be not just imposed on it, but you want it somehow to be intrinsic to the object, so that when you twist things around, you still see this. And it turns out, actually, this is one of the big innovations that Misha Gromov made to the field, that you can, if you have a four-dimensional manifold, so it's a four-dimensional space that locally looks like Euclidean space, and locally it's got one of these symplectic forms on it, which locally looks like, in little pieces, looks like this measurement. So you've just got a twisted form of it. Then you can you can't quite locally identify the neighborhoods with neighborhoods of C2, but good enough so that you have some notion of what's called an almost complex structure on here. So you have some remnant of complex geometry in here. And that is an enormously simplifying idea, because it means that instead of looking at 4 disparate coordinates that could be twisting separately, you really only have 2 things to worry about. And it also means that you can look inside this object for particular, they're one complex dimensional objects. So they're curves, but they're complex curves, so they look like 2-dimensional objects, but they're sort of described by one complex coordinate. So you have these special things, so they're called submanifolds, in your manifold that are related to the complex numbers. And if you can find them, they give you a lot of information. And so there are theories for trying to find these things. Now, I have got perhaps another 2 minutes or something. There was one thing I wanted to tell you. There's one other way you can see the power of this idea, and that's through a sort of complex version of Morse theory. So Morse theory, if you want, is a way of trying to, in this context, is a way of trying to understand the structure of a manifold by putting a function on it. And the best example is to take a torus, which is a donut, And think of a function which is just what's called a height function. So at every point, if you think of this sitting in Euclidean space, at every point, suppose this is at height 0, so that's 0 on the line. Here are all the things which would, say, be at height 1/2. Here are all the things which are at height 1. And these say you've got things at height 2 which look like that. You've got, this is just a point at height 3. And in the middle here, you have 2 circles. These are the things that live at point 1.5. And what this function does for you is decompose your manifold, which is 2-dimensional, into a sequence of 1-dimensional things. And then you can understand how the structure changes. So you have a point, you have a bunch of circles, then you have 2 circles, and which are joined, and they separate, and they come together. So it gives you a sort of movie of what the manifold is like. So that's a real Morse function. Now, one of the recent discoveries, which was proven by Donaldson, is that in the symplectic world, there's an analog of this for complex Morse functions. So that means a complex Morse function would not take values in a line anymore, but would take, I mean, this is an interval, wouldn't take values in an interval, it would take values in part of the complex plane. So it would be a 2-dimensional thing. So it would actually look like a disk. So I suppose I can make my disk look like that. So there's my disk sitting inside the complex. And over every point, then, we have, you see, if you have an inverse image of a point, it's a 1-dimensional object. So if we have an inverse image of a point here, it's some 1-dimensional complex object, which of course is 2-dimensional real object. So what you have is a family of a 2-dimensional family. For each point here, you've got some real object which may or may not have singularities. You have this family of, what you're doing is taking your manifold, which was a sort of understandable 4-dimensional space, and decomposing it into a family of 2-dimensional objects. In a way, and the function it's giving you here is now a complex function. It's got some very nice properties. So these surfaces are these nice complex surfaces, these complex curves I was talking about. So that gives you a whole lot of structure in your manifold. It's reduced something 4-dimensional to families of 2-dimensional things, which are much, much easier to understand. And it's been a very powerful idea. Now, not all 4-dimensional manifolds have a symplectic structure, but it turns out that you can sort of adapt it and still make it, for arbitrary manifolds, make decompositions like this. And that's a very powerful way that people are now trying to understand 4-dimensional objects by thinking of those as families of 2-dimensional objects. Not all, I mean, there are certain singularities here, like corresponding to those things, but you have a way of, now you have an idea that allows you to start looking at structure, trying to make calculations and so on. So I think my time's up, so I'll stop here. Thank you very much for your time.